Hi everyone, it's Hassan Ali. Today I'm going to do an Abaqus tutorial again. So this is our exercise, right? A 3D beam, and we are going to simulate the bending force on this beam on the right face, and the left side is fixed. It's a fixed support that we are going to apply, and then we will compare our results with the analytical solution. I have a Python code here that I prepared that I'm going to use. So let's go and create our part. So click parts, you give a name, which is beam 3D deformable in order to have a realistic behavior, solid extrusion, right? Continue. So we can see the dimension here, 1 meter, 0.1 meter for the height, and for the width is 0.05 meter. So we are going to work on millimeter. It's fine. I mean, for Abaqus, it's better to work with millimeter because it's easier to work with the geometry. So I'm going to give a dimension. So 1 meter is 1000 millimeter. 1000 millimeter. The height is 100 meter, and the width is 50 meter. Okay, 50. This is what we have. And the second thing is for the property, right? I click property. It's a steel material. So for the steel, and the density is 7.850, for example, power of -9. Okay, because we're working on millimeter. And then elasticity, the Young modulus is 200,000 megapascal, and Poisson ratio is 0.3. Okay, and now we have our material. We can check on the manager. Okay, still, so it's created. And let's create a section 1 for the beam, solid, because we have a 3-part, homogeneous, because it's an isotropic material. We have a steel. Okay, it's not a composite, it's a steel which is homogeneous. Continue. Steel, we have it here. If you want to create another one, you can still click here and create. But what we have as a steel, we will use it. Okay, now we created this section, but we didn't assign it yet. I click here, assign section. I click my part, I hit done, and okay, we can see the change in color. That means the section has been applied successfully. Now let's go for the assembly. We always will do this, okay? Because it's to create the part instance. We need to do this in order to have our parts and work with. And let's go on step. The step is where you will define the kind of loads that you will apply. So the initial, which is already here per default, is for the boundary condition, right? You cannot use this step for the load. So because I'm going to apply a bending load, so I can give a name of my step like bending load. Okay, that's what I'm going to use for the bending load. And it's a static general because it's a linear static analysis. And I hit continue. The incrementation I can give like 0.05, and the maximum 1 is fine. I hit OK. Now I have my step. Let's go for the load, because interaction is if you have different or let's say many parts and you create contacts, that where you will define the interaction, the way they contact to each other. But we only have one part here, so let's go on load. So let's create the load here. We want to apply here on the right side. So we have pressure. That's not what we're going to apply. So in order to have the to define the direction, I think the surface traction is fine. Okay. So I will hit continue. I click this face, hit done. Now I want to apply, but the surface traction, remember, it's surface traction. So this is a pressure, not a load. So the 1000 Newton here is not what I'm going to apply. Why? Because this is a force and I need to apply a pressure. So I can calculate the area of this face and then I can divide the force by the area, and now we have the pressure. Okay, so if you do that, you can see that the area of this rectangle is 0.05 times 0.1. You have the area on meter square. You will convert it to millimeter square, and then if you divide the let's say if you divide the this, you will have the pressure on Pascal, and it will be 0.2. Okay, so 0.2. No, that's not what I'm going to have. I will have 0.2 megapascal. Okay, so that's what I'm going to apply. So 0.2 megapascal. This is our pressure. And then I click here in order to define the direction. So the apply force is going downward. Okay, so I click this point for the origin and this as the end. So now the software understood that it's -1 here. That means it's going downward. Okay, so you can even see here the arrows are projecting to the downward. So now we have the load, and then I can even click on manager to check I have it, and I can create the boundary condition. The one is fixed supports. Fixed supports. I will click the from the initial, right? I can even start from the bending load, but let's go from the initial. I think this is perfect like this. So if you go symmetry, I can apply encastre. I can even go on displacement rotation, so I will have more control in the way I define my fixed support. So I will click this face here. I hit done, and now we'll click all of this. I will check all of them in order to say that I'm blocking the translations, the 3-degree freedom translations, and the rotations. Okay, I hit OK. So now we can see everything is fixed. So let's go on mesh. So on mesh, I will click here, mesh, but it cannot work. You need to select part here first, and then you click. So 50 millimeter is a bit higher. We have large mesh. Let's go 25, for example, and I hit OK. So now I click here to generate the mesh. So this is pretty good mesh, and I will go here on the job, and I will click here and say for the job one, model one, I think this is fine. But before I do this, I need to go on the load or the steps. I think the load in order to check this boundary condition. So you can see here. So that means the fixed support start with the initial to the bending load. The fixed support is still activated. It's still used. So this is correct. Okay, I just wanted to check in order to be sure. So let's go on the job. I think we already created. Let's hit manager. No, we didn't yet. So let's go create job one, continue, and then OK. And then we can submit our work and wait for results. So now let's wait for results. So now the simulation is complete. Let's go results and hit this. We can see we have 9 megapascal. Okay, so 9 megapascal is the highest stress that we have, and the lowest stress is 0.2, 0.29 megapascal. So the region that we have the lowest stress is here, where we apply the surface traction, and where we have the fixed support, it's where we have the highest stresses. So this is pretty well. That's what I expected. And you can click on the animate here. You can see the way our beam is moving. So now we're fine. We can go and compare the 9 megapascal to our analytical result. So I prepare a Python code here for analytical result. I use every information that we had, and I will click here to run my Python code. I can see this is what we use, everything, and the maximum bending stress is this 12 megapascal. So I got 12 megapascal, And the numerical results are giving 9.67 megapascal. So this is not far away. So that's fine. I think the margin of error is 2 new megapascal. So I think this is okay. I mean, we can calculate the error. So yeah, you can do that, and I guess we have 0 point something per something as an error. This is the stresses. We can go for the reaction forces here, and yeah, we will have everything. You can also check the strain. You can also check the displacement here. So this is okay, and yeah, we can also create a graph. But if you guys are interested in the way we create graph, you can ask me, because we use this block here, create X data. That's where we go in order to create our graphs. So I think that helps, and peace.